Hi everybody, this is Professor Bankowski. In this video, we're going to talk about section 7-3, which is estimating confidence intervals for population proportions. To begin with, what is a proportion? Now, there's a number of different criteria that have to fall into place to make a proportion happen. The most important one for us, though, is going to be you have a situation that has only two possible outcomes, and only one outcome could be the true outcome. So the classic example of something like this would be a coin toss, where you flip a coin, you only get heads or tails, but you cannot get heads and tails at the same time. What we'll do is, before we get into math, before we get into calculations and formulas, let's just take a few situations and see if we can figure out, do we have a proportion or not have a proportion? And the first one says we're going to look at our neighbors, and we're considering the fraction of those people in the neighborhood that live in red houses. We could say that you either live in a red house or you don't live in a red house. And for simplicity, we'll pretend that you can only paint a house one color. So this would be a proportion, because you either live in a house that color or you don't live in a house that color. Next, we're talking about the percent of business owners who own restaurants. And if you are a business owner, you either have a restaurant or you don't have a restaurant. Yes, this would be a proportion. Okay, if we roll a die a number of times and we want to know the proportion of times, the times that we could get an even number, would that be a proportion situation? And a lot of students find this one kind of tricky, because we tend to think we roll a die and we could end up with a 1, 2, 3, 4, 5, 6. And of course, it's not a proportion, it's 6 different possibilities. However, the way the question's worded, when they're saying get an even number, we could box that into 2 different situations only happening. Either, yes, I got an even number, or no, I didn't get an even number. Technically, this would be a proportion. Percent of times that you will draw a club from a deck. Now, by just the same reasoning as before, if I draw a card, there's lots of different possibilities of what I could get, but I can put it into just one of 2 different outcome situations by saying I either got a club or I didn't get a club. Yes, this one would be a proportion also. Now, the last one is asking people which brand of coffee that they prefer. And many people could have multiple answers. They could prefer more than one brand, so this would not be a proportion. Okay, so now that we've seen a few elements of how this works, let's talk about our first symbol. We're going to write down that the population proportion is going to be P. Maybe we're interested in the proportion of students that will attend the BCC college's full-time students. So if we want to figure out what that proportion is, it might be a good idea to start by taking a sample out of the population. And then we can take a look at what's happening in the sample, study that sample, and generalize about the sample for the population. So if we have 100 students from the population, before we start to get into technical numbers and things like that, we're going to talk about something called the characteristic of interest. And the characteristic of interest is a special trait or characteristic that each member of the population either has or they don't have. For us, the characteristic of interest is that you are going to go to school full time. So what we're going to do is we're going to let X equal the amount of people that possess that characteristic of interest. And we're just going to go ahead and we're going to make it up and say that we have 35 people that are going to go to school full time. Now what we do is we have enough information to create a sample proportion. So we're going to write down that the proportion of students possessing that characteristic of interest is going to be 35 out of 100. And 35 out of 100, in terms of symbols, what we did was we took our X value and we divided it by our N. And that is going to give us our next most important symbol called P hat. P hat is going to be our sample proportion. So most of what we're going to end up doing is taking a sample and looking at the sample to figure out what P hat is and using P hat to estimate an interval for P. Now, before we see the formula, there's just one other small thing that we need to see. How many students won't register full-time for the fall? If we want to figure out the ones that don't register full-time, well, I know there's only two possibilities. You're either going to school full-time or you're not going to school full-time. And both of those outcomes, both of those percentages would have to together total 100%. So what I could do is I could take 100% minus 35 over 100, and that's going to give me 65 over 100. That's going to be the proportion of people without the characteristic of interest in my sample. And I'm going to call that Q hat. Mathematically, Q hat is going to be equal to 1 minus P hat. Now, most of the time, I'm not going to do that much work studying Q hat. I just simply need to know it from my formula. So let's go ahead. Let's take a look at our formula. It's going to be very similar to what I saw in section 7-1 and 7-2. I'm going to be taking a point estimate and adding and subtracting error to that point estimate to get my interval window. My point estimate is going to end up being a sample proportion P hat. And my error term is going to be the square root of P hat times Q hat divided by N, multiplied by Z alpha over 2. And something really important to pay attention to in the formula is we're going back to the Z tables. One of the mistakes a lot of people make is they use the wrong tables at the wrong time. And if you just did section 7-2, you might be inclined to start using the T tables again. But we're going to be using the Z distribution for our work with proportions. And this actually strikes some people as kind of strange because they'll say, if I'm just flipping a coin or I'm asking somebody, what color house do you live in? How does that end up being a normal distribution curve? It doesn't make any sense to me. And the fast answer is we have to take a whole bunch of trials of an example to see the bell curve happening. And we're going to take a few minutes to do that because it's pretty important to know the technology behind the formula. And then we'll go ahead and we'll have everything we need to know to actually work the formula. So we're going to start the technique of actually seeing the bell curve happen with a little example. If we were to go to a hospital and we're looking at 10 different pregnancies, our characteristic of interest is the number of baby girls that were born. So in my very first example, I'm going to do 10 pregnancies, and I'm going to write down a G whenever I find a baby girl birth. I'm going to write down B if I find a baby boy being born. So in this case, it looks like I have 8 out of 10 births that are baby girls. So I'm going to go ahead and write down that my P hat for sample 1 was 8/10. Now, I'm also going to go ahead, I'm going to make a number line. I'm going to write down that the least amount of baby girls I could have born as a fraction would be 0 out of 10. The max would be 10 out of 10. And I'm going to go ahead and put an X in the spot where my 8 out of 10 was. Now, I'm going to do this whole experiment again with 10 different pregnancies. And this time, it looks like I have 4 out of 10 births that are baby girls. So I'm going to write down that I have 4 out of 10 births, baby girls. I'm going to put a mark on the spot there for 4 out of 10. I'm going to do the experiment again. And my P hat for sample 3 is also going to be 4/10. I'm going to go ahead and I'm going to put in another mark above the 4/10 on the number line because now I know I have 2 instances where there were 4 out of 10 births being baby girls. I'm going to repeat the experiment again, and I get another 4 out of 10 for my P hat. And I'm going to keep on doing this over and over. I've got 5 out of 10 baby girls, sample 5, and another 5 out of 10. And then I have 3 out of 10. And what's going to happen is if I keep doing this experiment over and over again, tons and tons of times, all of a sudden, this is what's going to happen. And we might look at this and say, oh my goodness, I recognize this. This is a normal distribution curve. It looks like if I drew an outline over the shape of the x's, I would end up with a normal distribution. Now there's something that's really special at the center. The number that's written in red, 5/10, what that's alerting us to is if we went ahead and we calculated the average of all the P hats, we get back exactly the population proportion P. If we calculated the standard deviation of all the P hats, we'd end up getting p hat times q hat divided by n under a square root sign. And I know the standard deviation can be a little bit kind of funky for people if we're thinking about what it's doing. All it's saying is that if we go back to all of the p hats that we had and we calculate the standard deviation of all these fractions, it would be exactly equal to what we get when we take the number for p hat, multiply it by q hat, divide that by the sample size, and take the square root. So having seen all that, this is just a reminder of what our formula looks like. Remember, we're going to use the z distribution, not the t distribution. And we're going to go ahead, we're going to walk into our first example. So take a minute and pause the video, read through the example. Okay, so inside of my example, first thing I'm going to do is I'm going to go and write down all the different numbers I've been given here. And now I'm going to go ahead and I'm going to start to identify things. If I read through the question, the first thing they told me was that they were looking at 763 adults. Now, when they say they're considering a total of 763 people, it looks like that's probably my sample size. So I'm going to go ahead and mark down 763 as my n. The next number they gave me was 329. And they said that those 329 people would travel to outer space in their lifetime. And if we think about it for a second, that's kind of like a question that you could ask somebody. Would you like to travel to outer space in your lifetime? Yes or no? So it sounds like that's our characteristic of interest, because it's a situation that has only two answers. Yes, I want to go to outer space, or no, I don't want to go to outer space. So it's sounding like 329 belongs to my x value. That's going to be my characteristic of interest. Okay. They also gave me 92%, and that's probably going to be used for my confidence level. My z values are going to be plus or minus 1.75. Now, if you're not really sure how I got the 1.75, I'm going to take a minute to walk you through how I found that. And if you feel good about coming up with that, feel free to fast forward the video. So I'm going to bring up our next screen a little bit early here. Okay, so what I did to start with is I just took my confidence level and I put it right in the center of my bell curve. And what I need to figure out is, what's my alpha level? How much area do I have left in both tails? How do I do that? Well, I know the total curve area must be 100%. So I'm going to do 100%, or 1 minus 0.92. That's going to give me 0.08. And now I need to know how much area is in each individual tail. So I could take my alpha, I'm going to divide it by 2, and it's going to let me know that in each tail on the left side, on the right side, I'm going to have in both tails 4%. Now I need to go to my z tables and I have to track down what's the z score that's coming to, that's matching with the closest number, rather the area closest to 4% of my z tables. And when I identify that, my z-score is minus 1.75. I'm going to go ahead and mark on the left side of the curve, my z-value is equal to minus 1.75. So my right side must be 1.75. Now I'm going to walk back to where I was in my previous slide. And I'm going to go ahead and bring it right back to where we were before. Okay, so our z-value was plus or minus 1.75. Before we can get into our formula, though, we also need to find our q hat and our p hat. So my p hat, of course, will be x over n. That's going to be 0.431 from 329 divided by 763. My q hat is going to be 1 minus that number, 1 minus 0.431. And that's going to be 0.569. And now I have nearly everything I need to fill out my formula. So I'm going to go ahead. I'm going to put my caret mark back on top of q hat, and I'm going to bring up my formula, p hat plus or minus my error term. Pause the video for a couple minutes and work out the computation, and let's see what happens. Okay, so for my left side, when I fill out everything, I'm going to end up with 0.4. When I fill out my right side, that's my number that I'm going to end up getting. When I put all this together, what can I say? Well, my photo finish is going to be that I'm 92% sure that between 40% and 46.2% of the people would like to travel to outer space in their lifetime. Let's go ahead, let's do one more practice example. Okay, so take a minute and stop the video, pause the video if you'd like to, and read through the question. Okay, so I'm going to go ahead, I'm going to list down everything that I've got to work with, all my different numbers, 50, 23, 90%, and I'm going to start to identify things in the question. They said 50 first-time whitewater canoers. So it looks like they were taking a look at a total of 50 people. That sounds to be like they're trying to tell me my sample size N. The next piece of information they gave me is that 23 of those people did not want to repeat the experience again. Well, it sounds like I could ask people, would you like to go whitewater canoeing again? Yes or no. So 23 is probably going to be my characteristic of interest, because they're saying that 23 people responded favorably. That means 23 is going to be my X value. For 90% confidence, that's going to equate to a Z value of plus or minus 2.58. The last thing I need to work my formula are going to be my values for P hat and Q hat. So P hat will be X divided by N. 23 over 50 is 0.46. My Q hat value is going to be 1 minus 0.46 will be 0.54. And by the way, a little kind of the safety mechanism that you can do. Safety check. Take your P hat and your Q hat and make sure they add up to 100%, because if they don't, it means that one of those numbers is wrong. Okay, having everything we need for the formula, let's go ahead and let's start to fill it in. Pause the video for a few minutes, see if you can work it out, and let's see what we end up with. The left side here is going to be 0.46 minus the error level. That's going to come out to be 0.344. Our right side is going to be the same thing, but with a plus sign, and we're going to end up with 0.576. If we put it all together, we're going to find out we're 90% sure that we're between 34.4% and 57.6% of those people who would like to not repeat the experience again. And I realize in the box it says go to outer space. That should say we're 90% confident that between 34.4% and 57.6% of the people would not want to repeat the canoeing experience again. And I hope this video was helpful. Thank you for watching.